Hi, everyone. My name is Cedric. I'll be presenting today with Stefan, and we'll talk about essentially how we've been using Julia at Planting Space, and also how we deploy the production app with Julia. So first, a few words of context. So at Planting Space, we are developing an explainable answer engine, and the idea is that we have some kind of web service where we can answer any kind of requests or incoming queries and provide statistical distribution as output. So essentially, we don't provide a single answer, but a set of answers ranked by probability. And the way we go about that is we take the query, and we have a system which will know about lots of different pieces of knowledge, and then synthesize an actual Julia function, given the query and the different bits of knowledge, the primitives that we have. And then run this Julia function with probabilistic programming to then have the statistical output. We do this so that we can have also a fully transparent reasoning. So you don't just return the answer or the answers, but you also return the procedure, including all the steps that were needed in order to derive this answer. So to build this, we're between about 35 people. We're all fully remote, scattered across different continents. We are still in the initial development phase, meaning we don't have like a product to be sold yet. We're still working more in a researchy development kind of phase. We're about 20 to 25 core developers developing this. And something to note is that, which is quite cool, is that all of our backend uses Julia. The frontend uses, well, TypeScript and JavaScript, but we'll be interested in backend here. So first, it might not be so obvious why we chose to use Julia in the first place. So let's go over the main points. First, it's really a high-level language. It's great if you want to prototype. And given that we're developing something really quite innovative, we do need to have some room for iteration on it. And Julia helps a lot with that. There's also that it's fairly simple language to use, to learn, to read. It's very easy to go through a code base written in Julia. We really love that. There's also the performance aspect, of course. With Julia, we know we can get performance when we need it and achieve as much performance as we need. And also, it's very well suited for just numerical computing, which is, we do a lot of numerical computing on the types of logic that we design. One other thing also is that we do tend to generate code a lot because, well, we generate an actual function. So that means you need to build some function and then execute that, like an actual Julia module. And for that, we use a lot of the metaprogramming facilities. And furthermore, we also use a few domain-specific languages for a few internal parts, notably, to really help a lot with productivity. And it's really cool that we can do this. There are a few downsides, however. So it's not as easy as, if you want to deploy something really quickly, you can use Python. You have a plethora of tools available to you. So there we need to put a lot, well, not too much effort, but quite some effort into developing some components that might not be so ready to use in Julia. There's also that given the type of product we're designing, we need a fairly low time to first answer, kind of time to first X for us. And well, we know that Julia isn't really made for very low latency applications, but there are ways to mitigate that, which work fairly well for us that we'll cover in this presentation. There's also one aspect, I guess, a more social aspect, is we don't have so many Julia developers out there to hire. And so when we need more hands, we essentially have to broaden our scope. And for that, we just try to find good programmers and then rely on the fact that Julia is fairly easy to learn. With also a carefully designed onboarding to get so that people can get up to speed with Julia and contribute quite easily to initial tasks. Now we're a bunch of people, as I mentioned, 20, 25 people around that, developing Julia code. And so the way we go about that is a bit non-standard, but a few organizations have done similar things. So essentially we have one monorepo, where we have all of the code mostly lives in one place, so it's easier to set up, to understand what is where is what. And then we also have one main package. So we don't have like multiple different internal packages. We just have mainly one. And there are a few reasons for this setup. The monorepo one is that it's just easier to, like if you want to make bigger changes, you don't need to scatter your pull requests across different repositories. You just have one. It's also easier to have just a continuous integration setup in one repo, not multiple ones. For the using only one package, one aspect is, as I mentioned, we have a very iterative development process, and sometimes even our core data structures need to be changed and iterated over. And it's just easier when you don't have to maintain interfaces between packages, like explicit interfaces. So things can kind of tend to move, and until they solidify, it's really nice to have some more flexibility in that regard. There are other approaches, of course, when you have a small to medium-sized team developing Julia code in an organization. You can have, for example, a monorepo approach, but with multiple packages. You can use a local registry or not. Depends if you want to use semantic versioning, notably, with compatibility bounds. You can otherwise use multiple repositories if you want to emulate some kind of open source ecosystem type of development, even though it might be proprietary code. So they have multiple repositories, maybe multiple developers working on different repositories each, and so on. So now, as we use this approach with a monorepo and one main package, we do need to make sense of the code. We have so much code that no single developer has a knowledge of everything that is in there. So we need to structure our code a bit. And for that, we rely on Julia modules, and notably on some modules for that main package, to design sorts of self-contained units of code where essentially have somewhat of an explicit interface between what a package imports, what it depends on, or a module, what a submodule depends on, and then what it can provide to other submodules with exports. And we are quite strict about this, so that then our code base is structured in a way that is really easy to understand. And it will be even easier also for us to analyze our code base and perform some form of code analysis that will be useful to develop a few tooling pieces. All right, so now I'll hand it over to Stefan, who will talk more about the tooling that we developed and also how we facilitated our workflows.
Yeah, hi, I'm Stefan. So as we just heard, our team is perhaps a little bit, so our repository is a little bit larger than the average, than the average Julia repository. And the other thing is, we had heard yesterday at the package analyzer talk that the average Julia repos contributor had about 2 contributors. So we have a lot more people than that, which meant that to work effectively, we had to build a few things here and there to make working together a little bit easier, and perhaps a bit sort of uncommon practices that I'm going to describe now. The first one, perhaps, is that we commit our manifest into our package. Normally, I think a lot of, like most packages use compat bounds, but that didn't quite work for us for a number of reasons. The first one is that we're building an application, not a library. It's only us that needs to use it. We don't need to be compatible with like a wide array of other combinations. What is important for us, that for all developers, the environment is exactly the same, which also means that we want to avoid accidental breakages. Like, even though compat bounds and semantic versioning has a very clear rules, sometimes maybe one developer has already loaded some patch version or like some patch update, and suddenly everything breaks, but not for the other developer who hasn't done it yet. So we commit the manifest to the repo, but we still want up-to-date stuff. So we just once a month roughly update all of our manifests, all of the dependencies in one go, run an extensive test to make sure that everything still works, and we just commit it in, and that is actually quite neat. There's some inconveniences involved in that. The first one is that we need to dev our main package by relative path in sort of sub-packages like docs or like a workbench/playground repository. And so that's a bit of a tedious process sometimes. Like, we're really waiting for this like sub-projects idea to enter into PKG. Would be really nice for our workflow. The next thing is that with so many developers, we really want to reduce testing time. We have everyone, basically 25 people-ish, working on one repository, and we have a fairly high number of MRs that we have many small MRs going in. So we really want to reduce testing time to reduce developer latency. And to deal with that, we have 2 things. The first one is monorepo usually comes with a large number of tests. We don't want to run all the tests all the time because usually only a small percentage of the code base actually changed in a given MR. So we really ideally want to run only the tests that are necessary to run, and a few details on this in a minute. And the other thing is that because we only update our dependencies every so often, we'd really only want to pre-compile them or like compile them as little as possible, maybe only just once. So using a system image, and I know there was a talk yesterday that basically concluded, system image, maybe just don't. But actually we had some quite decent successes with it. So the first one is what we call change set-based testing. Cedric was explaining earlier our module structure, which means we have these small submodules, very clear rules on you can only use exported symbols, and there's a very clear correspondence between submodules and testing files, which means that in this specific scenario, we can actually then answer a question that is usually very difficult to answer, which is, if you make a change, what has been affected? So in our scenario, if, say, submodule 10, something changed, and then we know that submodules 2 and 5 import symbols from that submodule, then we only need to test 10, 2, and 5, and of course the overall integration tests, to basically cover, or like have a fairly high confidence that covered all the changes that we made. It's of course a fairly conservative estimate, but in our experience it actually works quite well and really cuts down on sort of average CI time for a developer. So that worked really well for us. The other one is on the system image. I mentioned before we have a fairly large number of dependencies, don't want to precompile multiple times, and we only rarely update them. So it really makes sense for us to build a single system image with all the dependencies. Some of this was grown before 1.9. We actually might change this a little bit now that there's the package images available. But in our sort of small example, it only takes us about like 11 minutes, plus maybe CI setup to build this image, and it saves us, 3 minutes on every main CI run. That is not even to speak about CI on MR or merge requests, and that saves us 12 hours over the month. Doesn't sound like all that much, but also like it's a fairly small effort for actually an outsized reward compared to what we're doing. A few other small things here and there we do. The first one is what we call auto formatter. It's quite common that there's format suggestions, even in open source repos. That was a little bit too inconvenient for us because you have to accept all of them anyway. So if it's not really a choice, why even present it as a choice? Why present it as a suggestion? So we just go straight ahead and have a bot auto-commit any distances between, like any issues, like any differences with formatting that might not be there already. So that's very convenient for us. The other thing is, I was mentioning change set-based testing earlier. Obviously, the immediate criticism could potentially be that there's a risk here that we didn't fully cover some impact that a change might have had. So we actually have a stopgap here, which is a result of GitLab. I think there's also a talk tomorrow about GitLab CI, not by us, but I'm very interested to hear about that as well. But so in this context, what we can do is in GitLab we can run on the theoretical change of main if the current MR was merged already. So if that succeeds, we know that once it's actually merged, main will still be intact. And there we just run the entire test suite, but then we actually only run it once for each MR. And the last one is stochastic testing. We don't want to fix the random seed because that is not quite robust enough for us. It could be that somehow accidentally we have fixed the one random seed when it always works. And actually for, if we picked 5 other random seeds, it doesn't work for any of them. So we just don't fix the random seed. Every test run is different, which means sometimes it fails. And then we have built some logic around that to say, okay, how likely was this to happen? Like, was this a 1 in 1,000 event and we just run it again and then, then it passes and it's going to be fine? Or do we actually, did we actually break something in this test and now we need to diagnose a little bit more? Like that is, but still, there's still very much work in progress for us. Yeah, so this is in terms of tools and like sort of small bits and things here and there that we use to develop. So what does all of that lead to? Like, what are we trying to do with all of this effort? What are all of these tools? And that's the title of our talk, towards developing a production app. So what is our product and what are we doing with it? Oh, that was one too far. So the deployment overview that we have is that we have this system which is supposed to answer queries, which means we need to be really receptive to changes in demand. It might be that something has happened and suddenly a lot of users come in and that have some question about something that happened, or I don't know, a variety of reasons we want to scale very quickly. And this is why Cedric is saying we want a low time to first answer. We want to be able to very quickly spin up a work, and it needs to be ready very quickly to answer a question. It doesn't quite work for us to say, okay, we spun it up. Now someone please sacrifice themselves to run the first query so we can get the pre-compilation out of the way. Like someone has to live the 1.5 minute or so that it takes to pre-compile. We'd really want to be quick about this. So to do that, there's some system image involved, which I'm going to talk about in a next slide. But the broad infrastructure for our product is that we have this Docker image, which we deploy in AWS Lambda, which contains the component, a first component to listen to potential requests. We've reverse engineered here a little bit the AWS interface, and it's basically just built on HTTP, waits for the next request to come in, and when one comes in, dispatches to our underlying Julia load, or like our underlying core product, computes the result, and then sends it all back. And yeah, so this system image, actually, we initially used to use Amazon Linux 2, but there's some issues with that, so we actually built our own custom Julia image based on the official Julia Docker image that you find on the Docker Hub if you go on the Docker Hub and search for Julia. So we just built on top of that and put in the right sort of components to mimic all the other things that more established languages like Python have in their Lambda-specific Docker image. Yeah, so what else do? We have obviously these components that are just needed to make AWS Lambda work. How to make it fast? I mentioned the system image already, so that is effectively the main secret sauce in a way. Again, there is the word of system image, maybe just don't, but the results are actually really good. Like if we just use our core application, and then I've normalized the plot on the right. With no system image, it actually takes quite a while. Then if we just add a system image without anything else, then actually we get like barely 5%, or like maybe actually it's less, like 3% of speed up. Still not really worth it. But then the secret sauce comes in with the trace file. So we actually have a fairly substantial trace file from our unit tests and some additional tests that we built. And if we include those into the building process, it takes a lot longer, but our first query is only like less than 10%. In terms of time cost compared to not doing that. And I really should have plotted here time to second answer, because that is actually pretty close. Like we're actually in a position that where like first and second answer are fairly similar in terms of time. So our coverage for these trace files is pretty good. We also removed, and this was like nice improvements in sort of recent Julia versions, that you can strip out more and more components from the Julia binaries to sort of reduce size and bloat. And then we also set some specific architecture flags to like just squeeze out a little bit more performance here. And then once all of that is done and all of that is deployed, we actually want to be able to monitor things. That too is a little bit non-standard. There's not so many tools out there as there are perhaps for other languages, so we had to hack a lot here. But broadly, actually, it turns out it's not so difficult. We're hoping to like that maybe eventually, maybe with us, maybe with someone else, this could be a bit more formalized. But we'll see how that goes. Until then, we basically just use a standard logger and log out in JSON, which can then be pushed to OpenSearch for structured logging. We export some timings to OpenMetrics, like in the OpenMetrics format, which is then pushed to Prometheus push gateway. Also works fairly neatly, because then we can visualize all of that in Grafana, and all of these three are standard DevOps tools. And then here we see an example graph, and these are sort of like the stages of our process, and we can really monitor how much time each process takes. So if something goes wrong and suddenly we have a performance degradation, we can really see, okay, what component broke? Is it pre-compilation? Is it just runtime? What do we need to debug? What do we need to change? We get really sort of real-time feedback on that one. And yeah, so that is sort of all of the components put together. And now I hand back to Cedric for sort of a small example of how this all can look in total.
Thank you. So we wanted to really talk about all of the different components that are needed to actually deploy an application in Julia and go in detail about, okay, how do you interface with AWS Lambda, for example. But we just don't have enough time to talk about all of this. So instead, we thought we would make an example project available so that you can take a look at it in greater depth after the talk. So it's essentially just a project which showcases a fully deployed Julia application with some very basic logic, but at least with all the components that you would need if you were to deploy your own application. So the idea is that then you can take this and take some inspiration from it, learn from it, and tweak that to your own tech stack. So it's a fairly simple application with 3 endpoints, one being some kind of test endpoint, the second being an endpoint that might allow you to test the peak floating point operations of your worker. I don't know, maybe you want to do that. And then the third point would be about just the application logic. So let's say you have some eval endpoint that evaluates arbitrary code. That might be the application logic. Of course, don't do that in a real application. And then to query any of these endpoints, you just use curl and query any of these URLs, and then you're done. You get the answer returned, and that's it. It's all deployed and answered your query or your So how does it look like? Well, first we provide a few different components for you that you can take a look at, which are quite useful. One is all of the pipelines that show the different stages for deploying, for essentially building the Docker image and then using some infrastructure configuration to deploy that to the cloud. Then you have, for example, the Docker file to really see how do we deploy, how do we build a Docker image for this application, and including any solutions that you had to use to reduce latency. So here we also build a system image. We essentially just install Julia, the repo, build a system image, and that's it. Then you have infrastructure configuration files. We use Terraform, which is fairly standard to describe all the infrastructure resources you will need in a text-based format. So it's much easier to manage, and you don't have to click through GUIs, for example. So here is one such file to configure the Lambda for deployment. Then you have the source file, which contains all the integration with the AWS Lambda runtime, which you would need to re-implement yourself, because as Stefan said, we don't have any such solutions for Julia supported by AWS. And then we have also a test suite that emulates some of the components that you would typically have in a deployed environment, so that you can at least test your application, make sure that it works, and when you deploy, you don't have nasty surprises. A nice side effect of testing that also is that when you build a system image with all the test suites run as a pre-compilation execution file, then you also get traces, so you can make sure you compile all of the parts that you need to reduce the latency to a maximum. And then, of course, you have the GitLab CI file you can take a look at. We have a basic testing job, but mainly a deployment job, which again builds the Docker image and uses Terraform. And we have the auto formatter that we set up for this repo, because why not, which Stefan talked about. All right, so to conclude, we essentially presented the way we've been using Julia at Planning Space, how we used it. Then we went on about describing a few pieces of tooling that we developed to facilitate our workflows and different issues that it solved. And then we showed how we would go about deploying a production app with Julia, but notably making available an example project for you to take a deeper look at it. Before I finish, I will mention that we are hiring a Planning Space. So if you might be interested in talking with us, please don't hesitate. We'll be happy to hear from you. You can scan this QR code and see the job openings. Otherwise, if you have any questions, you can come and see me or Stefan. We have also Luca and Theo and JuliaCon this year. Or just email us at talents@planningspace. Thank you all. Any questions? Yeah.
Hello. Hi. Thank you very much for the talk. So I have a question on the way you structure your entire code base. You said you have a single repo and you just have submodules, right, instead of packages. So does each submodule have an API? And what happens if different people working on different parts, and if some API changes, since they're not packages and you don't have semantic versioning, how do you deal with that?
So we don't have an explicit API beyond what is imported, what is exported. It's meant to be quite flexible. And so you can just read, okay, we have a submodule, it uses that, exports that. And then people will typically make changes to maybe different submodules. We don't have, the whole point was that we don't need to have an explicit API as you would with packages, for example. And so there, we can actually just recode, we write some bit of documentation, and that's worked well for us.
Okay, thank you.
Hello, I have two questions for you. The first question would be, with the advent of Julia 1.9 and precompiled tools, do you think they may be able to reduce or eliminate the sys image? Second question would be, if you can go into more detail, what problems you found with Amazon Linux. Were they Julia associated, or were they more on the AWS side?
Yeah, so the 1.9 changes we haven't fully tested yet. So all of this system image machinery was built before then. And we've benefited from the 1.9 changes on parallel building, because now actually system image can be partially multi-threaded. So we've seen a bit of a speed up there. But in terms of using package images that are now available, then we have some ideas, but we haven't had time yet to actually focus on this, because the current system works well enough, and there's other things that are not working well enough. So we've been focusing on those. In terms of working with AWS, it's reasonably well. It works reasonably well. I think the main problem really is hidden. It's things here and there. For example, I was saying we couldn't use Amazon Linux 2, which is the standard operating system for Docker images in AWS on AWS Lambda, because that ships with GCC from 2017. And if you want to build system images, maybe outside with a multi-stage build, then suddenly you're actually using a more modern GCC, and then things suddenly break in weird ways. Yeah, it's basically broadly, it all looks like it should be relatively easy, but then in the specifics, it sometimes gets a bit weird. Yeah.
Thank you.
Any other questions?
When you showed the application startup time, did that include the time to spin up the Docker image?
So the bar graph was from local experiments for me. So that's not. So that's we basically have some we built it so that we could mock it locally. So that's where the results are from. For the Lambda, we have what is called provision concurrency. So we always have a few hot images running. So they're currently fairly quick. In terms of startup time, it is reasonably fast. When we do experiment with this a little bit, we're talking 10, 15 seconds to realize that it needs another one, spin one up, and the init function. Most of that is actually loading the system image. I don't know if you've ever built a big system image, but when you do, and then you start off Julia with this big system image, it takes a couple of seconds longer than usual to start up, and that's, I think, where most of the time comes from. Yeah, I think we're also running out of time. I don't know if you have time for more questions.
Could you elaborate on the bar plots? If the scale of absolute time of the whole application is?
What the scale is. So here I normalized it because I did it locally, but we have a hard cutoff time of 30 seconds. So we have a hard cutoff of 30 seconds, and what we usually find with our queries is that if we don't do this well, we run around 35, 40 seconds, which is just a little bit too long. So basically, yeah, so the bar that you see here, that's one, is sort of around 30 seconds-ish. And then when we actually do it well with the trace files, we're talking like 5 seconds or less to get back on a query, like for the first time.
Okay, thank you.